soon. I will emphasize on some point again. The point is that you need to join the meeting using your SKU account rather than your personal account. So the recording started. Now we're supposed to start too. I'm a bit slow in my progress with the slides. I believe I stopped somewhere here with the anomaly and the description of the anomaly, what we mean by an anomaly, and what's data reduction, or somewhere within these two slides. There are slight modifications I made with those slides. I updated them, and the updated slides, uploading them again to the module, course module. I find still some students registering. Today I got a new students in the course. So the total number of students right now is 58. The majority of the students are from petroleum engineering. The rest are from the earth science. There is, except few students, I believe, probably only one left from the College of Agriculture. So what is anomaly in geophysics? Usually when we do a geophysical survey where our object is to find an anomaly, something different than the surrounding, something have a physical property which is unique, which is quite different than the surrounding target or host rock. That's what we call anomaly. There are some techniques in geophysics, they don't show anomalies. And others like gravity technique, magnetic technique, usually we are interested on anomalies. And we need to do data reduction before observing those anomalies. Those anomalies might be hidden if we haven't done data reduction. If we refer back to the data reduction, what I mean by data reduction, it's basically to present the data in beta format, in a format where only noise, some noise, and also the thing or the signal related to the geology is preserved. We do reduction because topography, for example, the Earth's surface is not flat, is not horizontal. There is uphills, downhills, valleys. Those surface features, they affect our readings. And we need to get rid of them to bring the data in better format, in better shape, in a geological meaning. That's what we mean by data reduction. Also, when I talked about that, we said that the gravity readings you take in the equator is different than the gravity reading you take at the poles, or either north or south poles. The reason being there is a centrifugal force. Earth is rotating around itself, so it creates a centrifugal force. What centrifugal force is the tendency of the Earth to push away things at a higher rate or at a higher force at the equator compared to the poles. So people usually feel themselves lighter at the equator compared to the poles. Your weight is higher at the poles compared to your weight in the equator. Whereas the Earth, or probably the same geological feature, supposed to have the same weight. If I measure two exactly the same rock, either in the equator or in the pole, I supposed to have the same weight. Two rocks of the same density. But there is variations. Those variations are not of geological reasons. I need to get rid of them. The way to get rid of them is called data reduction. And that's what we do with the data reduction. Again, we'll come back to this figure so you see what's happening with this profile or with the anomaly. Profile actually is a line we take measurements, geophysical measurements along. And each point we take a measurement is called a station, a measurement point, or usually a station. Station spacing is defined by usually yourself. Oh, sorry. Yeah. Let me show the slides. Started presenting. Yeah, you should have talked about that earlier. Anyway, I can see the slides right now. Is that good? You see the slides right now?
Good.
Thanks. Dream, she's saying that she cannot see the slides. Dream, can you see the slides? Uh, can you see the slides, Dream, right now? Okay, I think she sees them right now. So here what we see that there is an increase in gravity anomaly or gravity value, and the increase is due to the instruments or the station being closer to the center of the Earth. The closer you are from the center of the Earth, the higher the gravity value. And we see this tendency or this trend, and the trend is following the topography. Once we remove the topographic effect, we'll see that the anomaly is very clear. The anomaly is created because of this target or this dike or this intrusion, whatever it is. So usually we do reduction, data reduction to come to these points. If there is any extra noises or the data stay not clean because of outside noise, we go to the next stage, which is signal and noise. We try to separate the signal from the noise. So what is signal? Signal actually is the thing we want to measure, is the thing we want to keep, is the thing we are interested on, is the thing also related to the geology. Whereas the noise is the unwanted part, is something coming from outside source, is not from the earth itself. It can be from the earth, probably. It can be from the earth. In case if it's from the earth itself, it's called coherent noise. Whereas if it's from outside the earth, it's not of geological source, it's a random noise. I give you an example. The example I already showed to you when we were discussing the seismic. Where is the slide? Yeah. So you see primary reflections. What's the reflection? We'll come back to this. Is the real thing we want, is the signal we want to measure. But there are some multiple reflections. Multiples are noises. Those multiples are actually coming from the geology. Geology itself is creating the multiple. Even if there is no movement, everything is so quiet, there is no noise at all, we still will generate multiple reflections. And to remove those multiple reflections, we go do processing. Whereas someone is moving on the surface or some car passing nearby, they generate their own waves. And those waves will interfere with our recording, with the signal we measure. And that's the thing we call random noise. It might be happening at some point of the time and might not happening in another point of time. Whereas multiple reflections will always appear, will always be there. So back to the slides of signal and noise. Though the signal is the thing we want to keep, we want to measure, and they are temporal as well as spatial. Yani maybe the noise is higher at one place compared to another place. That's what we call spatial. Maybe it's higher at specific time rather than the another time. Maybe it's windy nowadays, so we might postpone the recording. We might keep the recording at some other point. And there are, for example, in magnetic surveys, there are some days where the magnetic anomaly is so abrupt, it changed so quite or drastically. On those days, we will not do any magnetic survey. Those days are called magnetic storms. So we don't do magnetic storms on magnetic survey during the days whenever there is a magnetic storm. What's magnetic storm? We'll come back to the point later on. So the signal and the noise itself, both of them are temporal or spatial. Understanding the noise is as important as understanding the signal. And how we distinguish what is exactly the signal and what's the noise, what I'm interested on, what I want to record, what I want to consider as the signal, it depends on in your objective, on the survey type you are doing. So for example, we have a case study here. We have a profile, and the geological model shows that there are some dikes in the sedimentary layers. Those are the layering sedimentary layers. There is an overburden and weathered layer we have. And before the dike, there was a granite intrusion. You see the granite intrusion. If you do the dating, the first thing happened is the layering. Then the layering were tilted. Then what happened? There was a granite intrusion. Later on, dike intrusion, and there was erosion. Finally, there is a deposition of the topmost layer. So what the granite creates, granite is probably of lower density than the sedimentary layers we see here. So it's creating this trend, this broad trend of low anomaly or negative anomaly. That's a negative anomaly. The anomaly can be positive or negative. So I'm having a negative anomaly. Whereas there are some spikes. I've seen some spikes. Those spikes are generated because of the dikes. The dikes are of higher density than the granite. Maybe basaltic rock. This is a granite. The dikes are basalt. So they create these high or abrupt or spikes in my anomaly. So they can be considered. If you are interested on finding the granite, those dikes, the signal from the dike are considered as the noise. Whereas if you are interested on the dikes, if you want to find the location of the dikes, then the dikes are the signal. If you are interested on the dikes themselves are that signal. So what's signal and what's noise depends all on your objective. If I go back to the seismic slides, you remember when I said that the Rayleigh wave is a noise in seismic reflection? Some people, whenever they want to do a seismic survey, their interest is Rayleigh wave. So the Rayleigh wave is the signal, whereas the primary reflections are the noises. And sometimes I'm interested on shallow surveys. Shallow survey, the refraction is my interest, whereas the reflection are the noises. For deep surveys, for oil exploration, for example, reflection method is the primary method, is the most common method. Reflection is the most common method for all exploration. So it's the signal, it's the target, it's the thing I'm interested on. Whereas the refraction and Rayleigh wave, love wave, air wave, they're all noises. I might ask someone a question. Basma, how are you doing, Basma?
Yes, Dr. Basima.
Basma, sorry. Basma, what do you think of airwave? What's the speed of airwave?
Airwave.
Yes. What's the speed of wave in air?
It's depend.
It depends on what? It does not depend usually, it's just one value. So the air wave is 300 or 330 meters per second. And you can clearly see it in seismic section. We'll come back later on this point when we discuss seismic method. So air wave have a speed of, or wave in air have a speed of 300 meter per second. Whereas the speed of wave in water, in pure water, is 1500 meter per second. You can easily recognize them in seismic sections. So you know that this is probably water, and that's actually an air wave. And how to, for example, if you're doing seismic survey or acquisition, seismic, you have your geophones light on the top, on the surface. How you avoid air wave? How you try to avoid air wave if you have an instrument? These are just random questions. You don't need to know them exactly. I'm just getting you interested in the course. So how to avoid them is can be done in one way. The way is that a geophone is something that has a spike and some small equipment. The spike, we put it in the ground, and the other part, the mechanical part, will be on the surface of the earth. The spike, مسمار, goes to the earth, be tied to the earth, and the equipment will be on the surface. To avoid air wave, we bore it. We dump some sand on top of yeah, so you can do what? You bring some sand and top, bury your geophones beneath the sand. And it's sometimes tough. When I did, for example, my training in Schlumberger, they were doing seismic survey in Abu Dhabi, and I did my training there, summer internship there. So the problem was the area is all desert, and the sand dunes, they keep changing they keep changing every day. The place you are right now, tomorrow is covered with sand dunes. So what they do to avoid the air wave, they plant the geophones and bury them with the sand. But the next day they come, they don't find where exactly their geophones are. They lost their geophones, and it happened quite often that they didn't find their geophones and they couldn't retrieve them back. And those equipments are actually very, very expensive. So airwave is a noise. Airwave could be in seismic reflection studies is a noise. To try to remove it from the best thing in geophysical study, to remove the noise at the acquisition stage. Whenever you are doing acquisition, try to remove the noise. Don't try to remove it when you are doing processing. If myself, I'm ugly, I'm very ugly, whatever cosmetic I put in my face, I will still be ugly. So don't think that, oh, let me collect garbage and do some filtering, do some makeup, and I get beautiful. No, myself, I'm ugly. Oh, that's my fate. That's how God created me. So why should I care then? Um, Keep this in mind. So try to collect noise-free data during the acquisition. If you are doing seismic refraction studies, for example, avoid movement. Tell everybody to stop, to be quiet. Don't move. Don't hit a hammer nearby. Don't do other type of acquisitions which can create disturbances or shaking into the ground. The best thing to remove the noise is during the acquisition. But there are cases it's inevitable. You cannot remove the noise. So in that cases, come then later on to the noise removal part or processing part, geophysical processing part. Try to remove noise then there in the noise or in the processing part. So here again, there is a case of a seismic record. Seismic is actually a wiggle. You see this, it's a waveform. It's a trace. Those are all the conventions we have or the naming we have of seismic. Because it's a shaking. I'm recording the shaking. Whenever the shaking arrives to the geophone, it arrives as a wave, a seismic wave. It gets recorded. So I have two records, two different types of record. We see that the first one is very clean, very clear. I know the onset exactly. Usually this is the amplitude and the x-axis is the time. So here I made a shaking. I start recording how much time it has taken for the wave to arrive to this signal. So it was quiet. The early time was quiet. It was, let me use the laser pointer. It was quiet all the time up until this point. So at this point, at this time, the wave arrived to the recording point or the recording instrument. Start shaking. That shake, how big is it, is the amplitude. If I make a bigger one, the amplitude of the shaking is higher. If I make a small one, the amplitude of the shaking is lower. Whereas the x-axis is the time. This is a seismic record. That's what we call a seismic trace or seismic waveform or a wiggle. They call it also wiggle. If I compare these two, I find the second one is saturated with a lot of noise. So how to remove the noise? There are many techniques. We'll not go to the details of how we can remove noises in seismic data, but because that's not the scope of this course. But these noises, how they are created? Because probably of random things, because of traffic, tides. There might be instrument noises. What are instruments? Instruments sometimes they can create their own noises. One of the instrument noises is 50 hertz noise. Yani all the electricity in Oman is operating at 50 hertz. If you have studied anything with electricity in physics courses, you know that the electricity, the frequency of electricity, at what frequency it's operating in Oman is 50. And you'll find this signal, this frequency noise at 50 hertz in your signal, in your traces. You need to remove them. This is very simple filtering actually. They can filter out this 50 hertz noise very easily in seismic signal. But there are other type of noises hard to remove, not easy. You need to come up with new ways, advanced techniques to remove those type of noises. But again, I will not cover them all in this course. There are different type of noises for different geophysical methods. For example, anything with seismic it's sensitive to vibrations. The root, for example, if there is a wind and the wind is moving a tree, the tree will create some shaking into the ground, and your instrument will record that. Even sea tides, the sea tides, they create noises. If I'm doing a survey in the marine, offshore survey, seismic survey made in the offshore, it happened quite some time in the Batna coast. You know what they do? They say all fishermen stop fishing that day. Stop fishing probably in 1 week because there is a seismic vessel or seismic crew doing seismic acquisition nearby. Don't do any type of fishing, and you find that the police is escorting them. Is trying to avoid any other ships to come nearby the vessel to avoid any type of noises. Vehicles probably they're all can create shaking, so these are seismic, they create seismic noises. Anything with electricity can interfere with electromagnetic surveys, electrical surveys. So different techniques are responding to different things. And sometimes it's not good to carry out two different geophysical methods in the same area. But sometimes it's fine. It's fine, for example, to have direct DC resistivity. With DC resistivity, we'll come back later on. It's fine to have DC resistivity measurement nearby seismic refraction. There is no harm at all. No one will be affected by the other. So it's good. But it's not possible to have DC resistivity with electromagnetic. It's not good to do DC resistivity with electromagnetic. Don't be afraid with those terminologies because we'll come back to them in more detail later on. What is DC resistivity? What is seismic? We'll cover more in detail what are. The point here is that every method is sensitive to different type of noises. There are many geophysical methods. Every method is sensitive to its own type of noises. And some of these methods, they can be carried out simultaneously without being interfering each other. However, there are other type of geophysical methods which can be conducted at the same time without any problem. Is that clear? I think so. So what's the best way to improve signal? How I can improve the signal during the acquisition phase, especially if my noise is random, especially if the noise is happening at some time, it's not happening in other times. How I can then improve the noise and disperse or cancel out the noise. The best thing is called stacking. Stacking is simply doing the measurement again and again and again and adding them up. If you are, for example, if you are not accurate with your measurements, if you are doing like a lab study, a chemical lab study, or or physical lab study, the best thing to make sure that your measurements are correct, to give the same experiment to different people in the lab. Everyone will come up with an answer. There might be slight variations. Those slight variations are because of human errors. You were not very accurate during the measurement. You maybe added some extra little things by mistake. And to cancel them out, average the readings. Make a lot of readings and get their average. This thing in geophysics called stacking. The procedure is called vertical stacking. For example, if something is random, a car is moving nearby at some point, or the wind is blowing a tree. So what I do if I'm doing seismic survey involves, for example, seismic refraction survey involves what? Involves hitting with a hammer in a plate to generate some disturbances. The objective of seismic refraction is to know what is the soil thickness, what is the thickness of bedrock or unweathered layer. The people with from agriculture, they might be interested in these things. What is the thickness of the soil? So seismic refraction can help you a lot with that type of investigations. But maybe there is a noise. How to improve the signal then and suppress the noise is keep hitting, keep putting, taking the measurement again and again and again, maybe 10 times, maybe 15 times. But keep in mind that the more you hit, the more time you spend. And the time in geophysical investigation or geophysical acquisition is accounted as money. You're exerting more time. You're spending your time. Your valuable time is wasted. Instead of recording, making another recording, you are repeating the same recording. You're repeating the same recording, so you need more money. If you are asking a contractor, you are making talking with a contractor, you tell the contractor, oh, in the same point, make 5 recording, make 5 repeats. So he might ask for more money. More advanced or more complicated noises, they cannot be removed with stacking. For example, coherent noise, one of the coherent noise we came across is multiples, not primaries. In seismic refraction, there are some multiples we talked about. So the multiple cannot be removed at all by stacking, vertical stacking. I cannot do repeating and average the reading because it's not random. It's always happening. It's always there with my signal, something. So it will add up with the signal. It will add up also with the primary. To remove them, then we need more sophisticated, more advanced signal processing technique. And those noises, we consider them as coherent noise. Noise which happens because of geological reasons, not because of outside reasons, not because of probably a wind or car or traffic or human being is moving or an airplane is, even an airplane, when it's moving on the surface, it generates some waves, some disturbances, and the seismic instruments, they can record the air flying 100 of meters or thousands of meters on the sky. So here you see how it works, how vertical stacking works. And these are two different examples. We see the signal part is always there. It's always having the same signature. The moving down, moving then up and down. Again, the same signature. In this small part, the signal part. So if I add it up, it will increase. It will interfere coherently. Whereas here I see a peak, then a trough, then a peak. Peak is something moving to the left or to the right, whereas a trough, whereas in the trough case, the trace is moving to the left. So they interfere destructively. They might cancel out, whereas the signal will be boosted about a lot, and I take its average. The same case is applicable here. So I have constructive interference and destructive interference. But you cannot keep adding up. You cannot do a lot of acquisition again and again at the same point. At some point, how much effort you put, how much you keep hitting the ground, there is no more improvement. there is no more improvement at all. يعني in seismic refraction survey, 10 hits, 10 ground hits is the maximum I can do, is sufficient to do. Don't exceed that number probably, and you will find it يعني in our the instrument we have in our department, the seismic instruments. When I start doing the acquisition and the repeat survey, keep hitting the same point again and again with the hammer, I'll find that there is an improvement in the signal. But after some shots, there is no improvement at all. Whatever I do of acquisition or extra hits to the ground, nothing changes. So I need to stop. Don't waste my time furthermore doing any more repeat shots. What about the acquisition? When I need to do an acquisition and how I can characterize the noise, how I can see the noise, all of these geophysical methods, they have something in common. Go to the field without acquiring data, try to measure the noise level. Try to see the shaking within your traces before you hitting the ground with the hammer, or before you send a current to the ground. For the case of DC resistivity, we send an electric current to the ground. Don't send an electric current to the ground, or neither don't hit the ground, but measure the naturally occurring phenomena, or what is the wave or the shaking already available in the ground. So if the noise level is so high, is very high, it's better not to acquire data, because your data, the signal you acquire, will be of lower value or lower amplitude than the signal itself. Signal is saturating all your signal. The noise is supposed to be of lower level than the signal itself to make good data. But if the noise level is so high, it's better to don't acquire data. Don't acquire seismic data. And how you can characterize the noise, basically do or record the data without sending your signal and without hammering the ground. See what's the noise level, how much noise the earth is producing. You will find that traces are moving. You'll find the traces are not like straight lines. Those traces or waveforms I showed you, it's not one. Each instrument will generate its own trace. So in our case, we have 24 geophones. So 24 traces, 24 traces. What are traces? Traces are simply something like that. This is one trace. This is another trace. This is one trace. So in here, this is a trace, this is what trace. So each geophone, each instrument will create its own trace. And in the equipment, at least the one we have in our department, is made up of 24 geophones. We call them geophones. Their name is geophone, but we'll come back to this again in due chapters later on in our course. The point again, the thing I would like to emphasize, it's bad to acquire geophysical data whenever the noise level is so high. The signal is totally saturated with the noise. Then in that case, whatever processing you apply, you cannot improve the signal at all. Something like a garbage in, garbage out. You are recording garbage. Your final product is a garbage. You cannot do anything. When you give this data as a geophysicist to the geologist, to engineers, or to people from agriculture, you'll find they cannot interpret it. They cannot come up with some geological models of the earth. It's then a waste of time. As I said, during a magnetic storm, don't record geophysical data. So we finished with processing. We finished with filtering. We have our data clean, noise free. It's not totally noise free. There will be always some noise left, which cannot be removed at all. And it's fine. It's fine. It's better to move on than spend time doing the same thing again and again, trying to get the things very perfect. Life does not worth spending time on something to make it very perfect. And in oil industry, in whatever industry, that's the case actually. Don't waste of your time just on something you try to make it exactly perfect. It's impossible to make it perfect. Move along, come up with the final results, whatever the results are you have. This is something I give you for your studies too. An advice, you can put it for your final year projects or whatever projects you are working. Don't spend time on something you cannot bring it to perfection. So we move on. We try to make a model. We come to the point of model. What model is a simple representation of the earth in terms of physics, physical properties. We say the earth is made up of 3 layers. The velocity of each layer is blah blah. That's an earth model. Physics is interpreted as velocity in this case and number of layers. That's an earth model. If I'm doing like DC resistivity, the earth model I come up with is number of layers as well, and what the resistivity of each layer. So people from, for example, agriculture, they are interested in the resistivity of soil. The resistivity of soil is a reflection of the water content of the moisture in the soil itself. So in that case, you say how many layers they have, how many different layers, and how much is the resistivity of each layer. That's a model of the Earth. How you created this model is from the data you acquired. But the model is always a small version of the real system, is not exactly the same as the real Earth. There is always a variation or slight change between your model and the real Earth. It's a simplification of the real Earth. And in geophysics, as we said, how we can define the model is a structure defined by its shape, size, dimensions, physical properties. And those physical properties as either density, magnetic properties, velocity, uh, whatever else, like resistivity. And when I can say that my model is close to the geology, that's very important point. Whenever I say I'm happy with my model, I think the model is good model. That's come to the point of what we say forward and inverse modeling. We'll come back to the thing again. So here I have a gravity anomaly. I have a gravity anomaly. That's a gravity anomaly. So I have, if I zoom in, it's not very clear. If I zoom in, you'll find there are some points, some dots. This is the profile. That's the profile I made and the measurements along. And the points are the measurement stations along the profile. Whenever your line, the line which is continuous, is aligning, is perfectly along those points, it means your model is almost accurate. And why is that? Because when you go to the feed, acquire the data, those are the real data. Those are representing the real geology. You came up to the computer doing modeling. You feed up your data to the computer. You say the computer, I think the earth is made up of this model. It has a sandstone, it has shale and basement rock. Basement rocks are igneous or metamorphic. There is some granite. That's my model. Okay, computer, you know physics. You know how to acquire data, geophysical. Computer knows because you let the computer learn. You make those programs. The computer will generate this compute. You will use this model to generate its own data. It simulate. It make a simulation. It almost as if you are acquiring data, but using the computer. So the computer simulates your data, generates a curve, a continuous curve. So the dots are the observed values. The dots, why I'm not seeing them? Because they are aligned. The line is on top of those dots. The calculated values are the line, which is generated from your model. So I make this comparison. I make the comparison between the observed values and calculated values. If there is a match, that's a good thing. That's a good sign that my model is accurate. In petroleum engineering, they do something called history matching. History matching. I need a volunteer from petroleum engineering. Am I right? Do you do history matching? Hello, petroleum engineers. Reem. Oh, Reem. There are two Reem. Shamsa. Okay. Anyway, no one is responding to me. Maybe you are feeling asleep. But history matching is that you predict how much I produce based on some simulations. You say, okay, the earth is made up of this porosity, it's made up of this pressure, and they are all assumptions you make. They're all assumptions you make. And you say, okay, let's assume I start producing oil from the field based on my assumptions. The earth is made up of this structure, its porosity is that, its permeability is blah blah, and I make a history matching. I think for how long the field will produce and how much it will produce oil. This is something we call history matching in oil industry or in petroleum engineering. Then I compare this thing with my old data. What's my old data? I started production some long time ago. I will see if my model or my guesses, are they matching the real thing? The real thing I produced? In geophysics, we do something similar. I go to the field, acquire data, get some data, and I create a model in computer. And I'll see the model I create, what data they create, what geophysical data they create. They call those data calculated values. They are not real, calculated. The real data, the one I acquired from the field, they are called observed values. I compare them. So if my model, my guess is matching, there is a match, good comparison, it means the model is representing the real geology. Is that clear? Do you have any concerns with the point I made in here?
Can you repeat it, Doctor, please?
Okay, I will repeat it once more the last time. So what we do as geophysics in terms of modeling. Modeling usually done using computers most often, nowadays at least, because computers can simplify things for you. Whenever we do go to the field, we acquire data. We acquire data, geophysical data. Those data are representing a physical property. Let's assume this is the density of the rocks. The physical property is the density or are the densities of the rocks. I got observed data. I got data. I have them. I obtained them from the field itself, and they are representing the real geology. I don't know the geology because I haven't dug into the ground, but I have some geophysical representation of the earth. In my computer, I make a model, and my computer knows how physics laws play or how physics laws work. How I can, the computer knows because I program the computer. It knows how, if I give it a model of earth layers, each layer has its own density, it can also calculate for me the gravity values or gravity anomaly. The thing or the, the values I calculated from the model, from the computer, they are called calculated values. They are called calculated values because they are calculated from a simple model I made in my computer. And they take those values, calculated values, compare them with the actual values from the field, actual recording from the field. And they compare them, see how they look alike. If they are matching, if there is good match, not perfect, at least some good match between the two, it means that my model is a good representation of the earth. Is that clear?
Yes, Doctor, it's clear. But, Doctor,
Yes.
how does the computer know?
How the computer knows?
It
Because
is with data.
no, computers knows because how the computer knows? That's a good question. How computer knows? Because you tell the computer how physics works. What is the forward model? How, if I have different densities, different rocks of different densities, what is their observed anomaly? What is their, sorry, calculated anomaly? You program the computer to know that. You program the computer to know that. So computer make calculation. Okay, this is the model. You, from this model, you will get this data, this calculated data, because you put all the physics laws governing the gravity into the computer. We'll not come to this point. We'll never ever do these things in this course because then you are expert geophysics if you know these things. But I will at least give you an idea how geophysics works in general. That's how the geophysical techniques works. That's how we do modeling. And usually these things are done at how people are programming computers to make such calculation. They are done in master or PhD level. So you are not supposed.
You can like make it do it itself with artificial intelligence.
Without doing any artificial intelligence. It's simple. These things are done like in 60s, 1960s, 1970s. Artificial intelligence was available by then. The formulas, the equations. What made the artificial intelligence good thing right now is the power of computers. The computer in the last century became so powerful. So the things we were not able to do them by computers long time ago, they are plausible right now. They are possible. So we are referring everything to computers. And the equations which are governing artificial intelligence, they were available long time ago in early 19 like 80s, 1990s, or early this century. But the computers were not very powerful. Right now, for example, this is a simple computer. Let me show you. Task manager. This is my computer. It has how many cores? 12. 12 cores. 12. There are 6 cores actually. There are 6 cores, but logical cores are, yani this one core can do 2 things together. So how many cores? And so speed is so high, and it's right now the speed is 4 point something. It's so high. In early 2000, having one core or 2 core was like a supercomputer. And this my computer in 2005 was like a supercomputer. It's very powerful computer. And long time ago, yani, having 2 gigabyte of RAM is big thing. Right now, I'm having how much? 64 big gigabyte of RAM. I'm occupying that much. So this is almost a very powerful computer in all the standards. Nowadays, the standards, this is simple gaming computer. The computer they use for gaming. It has good graphic card too, NVIDIA GeForce 1980. So nowadays the latest is 3090. So powerful. The early nowadays is so powerful. It's so expensive too. Why it's expensive? New computers, why they're expensive, especially the graphic cards, because have you heard of cryptocurrencies? Have you heard of cryptocurrencies? Have you ever heard of cryptocurrency? Never, ever?
Yes, doctor, they use it for mining.
Yes, they use it. They use them for mining. That's true. So they use these things for mining. They mine these things. But basically, coin market cap. So let's see how much is it Bitcoin. It's almost $40,000. 40,000. In 2011, it was $1. One Bitcoin was $1. And nowadays, one Bitcoin is almost $40,000. It's keep increasing. So it increased in the last 7 days, 15%. Ethereum is mined a lot nowadays. Ethereum was used to be $200, $100. Nowadays, $1,600. So people are queuing up in front of companies, factories, just to get those GPUs. And they became very, very expensive. They became very, very, the recent one, at least for the gaming industry, is 3090. And there are more expensive one too, but I'm not the kind of guy who can buy them because they are very, very expensive. When I bought this one, the price I gave, I think, was almost let's say 200 Omani Riyals or 250 Omani Riyals I gave for this. This is quite old. It was like 2016 version. And every 2 years, the company name is NVIDIA, releases a new version, a new update or a new version at least. So the point again, why artificial intelligence became very popular is the computer power. The computer power became very popular. Nowadays, like mainstream computer, mainstream CPUs, they have 16. No, mainstream CPUs, they have 16 cores, 16. I have 6. And they are a bit cheap. Yani. How much you buy those 16 cores? You pay 250 reals. 250 reals, 16 cores. In 2005 or 2010, paying for 6 cores was almost $2,000 or $3,000, 6 cores. Nowadays, even 16 cores, imagine 16 cores, and each core can do 2 things. So there exists virtualization. This thing is called virtualization. So each core, one core, each core can do 2 things. And things are moved to GPUs. GPUs became very powerful, and they do artificial intelligence, deep learning things in GPUs rather than in CPU. And those things, they need a lot of memory, a lot of RAM. So the one I have, at least it has 64 RAM. Back to the questions, you said how the computer knows, because I program the computer. I give the equations to the computer, physical equations. Okay, computer, when I'm giving you this model, what is the data I get, geophysical data I get based on my model? It can be 2D, 1D, 3D. In this case, it's 2D, XY. So you give it this data, it says, okay, I have these different densities. The thickness of layer, each layer is that. The shape of each layer is that. It creates for you calculated data, the computer, based on your inputs. And you made a program. And that's something very important nowadays, Yani. When I ask a geologist or even a geophysicist, do you know any type of computation? They say, no, I'm not interested at all in computation. I don't want to make any computer programming or any language. You don't need to create a software, at least to know how to play around with MATLAB, for example. If MATLAB is not free outside SKU, outside in the educational institution, use probably Python or other programming, learn it, because even artificial intelligence nowadays, the technique of artificial intelligence, deep learning, big data, they are all based on some programming language. You need to have some idea how to program. And the only thing you can learn by yourself is programming, believe me. And you don't need any assist from anybody. Just go Google how to learn some basic of any programming language. Whereas you will not ever, never ever find a lecture like that. The lecture similar to what I'm giving right now in geophysics probably. Whereas compared to programming language, all of these are freely available either in YouTube or other websites if you are interested in programming. Programming is nowadays like the old days. If you don't know English, you are illiterate. Nowadays, if you are not familiar with programming language, you are also illiterate. Especially someone from a science or agriculture or even engineering background. I remember one day a PhD graduate joined the Occidental company. So Occidental company was doing 4D seismic. I think I remember his name even. His family, his tribe was Al-Kindi. He did his PhD in UK and returned back. So he was the only guy creating new ideas, new things using MATLAB, using a programming language, and they kept him. He rised in ranking in the company because he was teaching everybody. He was coming up with new ideas. even though he's a geophysicist. And not every program, every idea you can have it in, especially in geology or geophysics, you have it ready in some software, ready-made software or commercial software. And in the university I was studying in my PhD, they never ever give you a commercial software. At least in SQ we have all of them, Petrel, you name it, Coral Draw. They give you only free versions, or they say do it with a programming language. So again, the idea is that the computer does not know how to create anomalies or how to calculate gravity anomalies, but you model it. You tell the computer how it works. Again, in this course, I will not teach you how these things are done in reality, but I give you the idea how geophysics works in general. So computer will generate for you so we came to this point where we stop. Yes, this is good idea. So you see what here? You see another model, and these are my readings. You see the dots are the readings, and the continuous line is what is the calculated data. So the readings are the observed data, whereas the continuous line is the calculated data. And they are matching. My line, the continuous line from the model, is going along all these points. So there is a match. There is an agreement between observed and calculated. It means the model you created in the computer, and you ask the computer to create for you, to calculate the anomaly, to give you the calculated values, and you compare the calculated with the observed. If there is a good match, it means the model is representing the geology. The model you created is close to the real geology. But not always the geology or the modeling technique is that simple. And it never ever, it's a geological problem. It's geophysical problem. For example, if I give you this anomaly, I ask you where exactly is the boundary of this dike or this intrusion. Some you might say, okay, it might be here, it might be here. I'm not sure exactly because this is very broad anomaly. It's not very sharp like that. Not very sharp. So there are some complications with the modeling. But nevertheless, you get an idea. Oh, something weird in here, something abnormal in this area. Something beneath this point in the ground is different than the surrounding. The density is different. And if you have already a geological idea about the area, that there are some intrusions, you might correlate this anomaly with the intrusions you have. That's good about geophysics. And another complication is the noise. For example, the dike, if I'm interested on these dikes, or if I'm interested on the granite is the broad shape. This shape, if you get, if there is no dike, these broad dashed lines you get from the granite anomaly in case if there is no dikes. Whereas the dikes will complicate the modeling technique. The modeling will become quite complicated then if you have these dikes. How to assess or characterize the shape and the size of this dike is not easy thing then. This is what we call some complications. Another thing is the resolution. The resolution. So I have two intrusions. There are two intrusion in my model in the real Earth, for example, in the real Earth, not the model, in the real Earth. But my station spacing was large. So we already talked that the spacing will control the resolution. So if the spacing I use during the acquisition is quite large, as you see here, you will miss one of those anomalies. So the anomaly will go along those points. Your modeling will go along your calculated profile, inferred profile. That's the actual profile, but the inferred profile you get from the modeling will skip the individual anomalies. So you see two individual anomalies. This is one anomaly, the actual one. This is another anomaly here because of this intrusion. You missed them because you made large spacing. Maybe if you have, for example, point in here, another point here, another point here, and so on, you would not have missed the anomaly. You not have missed the overall shape of these two different intrusions. Right now, I assume, okay, it's giving me a broad shape like the dashed line. I make the assumption that it's only one intrusion rather than two separate intrusions because of the station spacing. So this is also complications. And you might say, why from the beginning I don't make it very dense, very small spacing? Maybe of you the budget you have, maybe if the time you have, you are time limited, you have to finish the project within like 2 days, you have to carry out as much point or acquire as much point as possible. So you make your grid space large, spacing from one station to another station large, and you might make them low resolution, and you miss some features. You miss some geological features because your station spacing is large. Apart from that, there are other things, other theoretical or practical limitations. And one of these things is velocity inversion. In seismic refraction, we'll come back to this point. In seismic refraction technique, if you cannot do seismic refraction unless if the velocity of the deeper layer is higher than the velocity of the upper layer. And first layer has lower layer velocity, higher, and so on. In the seismic refraction case, you cannot do seismic refraction except if the velocity is increasing from top to bottom. If there is a layer of lower velocity than the upper layers, you cannot do seismic refraction. You cannot do modeling. You did seismic refraction. You went and did seismic refraction because you were not having any idea that one of the layers is having lower velocity than the upper layer. Your modeling is wrong. That's a complication with the modeling. This is an inherent problem with geophysics. This is one example, velocity inversion. There are some other examples with other techniques, not basically seismic refraction. Seismic refraction is a technique. We'll come and consider it and study it later on. Another thing which is very, very important, and it's quite common in passive techniques or gravity and magnetic technique, something we call non-uniqueness. Non-unique. There is no unique solution. Many different models, they will give you the same response, the same model, the same, calculated value. Many different models give you the same values, calculated values. So which one is the correct one. So in this case, for example, this is my calculated value. The one you see here, the red curve, is the calculated value. If I make my model only this one and remove these two, the lower one, I still get the same value, the same calculated curve. The anomaly is still the same if I take one of these possibilities. First, second, third, or even this small dot. I go deeper, increase the density. This is gravity anomaly. If I go deeper, make it smaller, but increase the density. Go deeper, make the model or the change deeper, or the target deeper, and increases density, I still get the same anomaly. This is called non-uniqueness. Yani there are many different models which give you the same calculated data. And you try to compare your calculated data with the observed data. But there are many different models. So which model is the accurate model? In geophysics, we sort two different techniques. Then I will not come or discuss them right now, but this is an inherent problem in geophysics with which is called non-uniqueness. There is no unique solution. Many different models agree with your observed data. Many different models are plausible models. More than one results is the same, is giving you the same results. Non-uniqueness يعني in math, for example, what's non-uniqueness in math? يعني what is, give me two values with which will add up. If you add them up, will give you a result of 4. 2 plus 2, 3 plus 1, 2.5 plus 1.5. It's an infinite. There are many possibilities which give you the same result, 4, if you add them up. So which result is the right result? Which result is the right? All of them are correct, but one of them is the true one. Maybe the one of them is the real geology. One of the model you created is similar to the real geology. How you can tell? In that cases, there are many other techniques, but one possibility is go ask geologist. What do you think is possible? What do you know about the area? What is more likely to happen? Do you find any outgroup which can be correlated with your model? Geologist can help you in this regard. But again, non-uniqueness is quite common in potential field. What are potential fields? Potential fields are gravity method and magnetic methods. They call them potential because those phenomena are naturally occurring phenomena in the earth. I'm not injecting something into the earth. I'm not putting any source into the earth, like the case with seismic, electrical or electromagnetic methods. So it's common in gravity and magnetic cases, but it's not very common in seismic methods. Seismic method, there is least likely that there is non-uniqueness. You usually come up with a unique solution with seismic techniques or electrical technique or electromagnetic techniques usually. So non-uniqueness is very important. Means that many different models can give you the same response, the same anomaly in simple like language. Resolution is another complication. You see, in this case, your data points, those dots, small dots, they made them like in circular case or circular shape. This is actually the D is the real thing. I'm trying to model it using different grading technique. This is one of the grading techniques, and the points are like that. The stations or the measurement points are like that. In this one, I have a regular grid. This is a regular grid, and the spacing between X and Y is the same. So this is a regular grid. This is a random grid. There are just few points. 1, 2, 3, 4, 5, 6, 7, 8, 9. Only 9 stations. 9 points you have went and took measurements on the surface. This will give you totally different than the reality. This is also quite different than the reality. This is the reality. But which one is agreeing the most with the reality whenever you acquire the data in good resolution? The resolution we said is a factor of what? A factor of data points, spacing between the measurement points, XY spacing. So B is the one which is most agreeing with the D, the real one. We come to the point of forward and inverse modeling. I discussed this thing slightly when I was discussing the modeling part. What is forward and inverse modeling? So we talked about modeling, but modeling itself can be compartmentalized or differentiated into two parts. One of them is called forward modeling. The other one is called the inverse modeling. So the forward modeling, what is it? It's the same question as Malik asked. How computer knows how to generate data from a earth I made. What is the earth I made? I made a model. The model is simply some layers. Each layer is made up of different densities or different velocities. If I'm doing like gravity survey, then I have different layers. If it's 2D or it's 3D. In case of 2D, just assume a section, 2D section. Each section has a thickness of layers and the density of each layer. So if you calculate the data from the model, I have a model and calculating data, the computer doing that, this is called forward modeling. This is called what? Forward modeling. Forward modeling is basically you give computer some data, some model, so not data, so some model, it will produce the response. The response is the data. Gravity anomaly. Inversion is you acquire data from the field. Inversion is acquiring data from the field and converting the data to a model. It's called the inverse. And usually how we work it in computer, we discretize the earth. We say the earth is made up of many small cells. Is made up of many small cells. Each cell has its own density. And it's simple to calculate an anomaly, gravity anomaly from small cell, small XYZ. Is made up in 3D sense. In 2D sense, it's just XY. So you know how to calculate gravity anomaly from simple cell. We discretize, make the earth small cells. And how big the cell you make them defines the computer power, how long the computer will take to do inversion or modeling, forward and inverse modeling. So if you make them smaller cell, the inversion takes longer time. the modeling will take longer time. If you make them bigger cells, the inverse and forward modeling will take lower, shorter time actually. So each cell represents one value, one density value, and that density value will give you an anomaly. And you calculate the anomaly from all the cells and you add them up. You add them up, you create your calculated data. You calculated data. So inversion, whenever you have data, you want to bring a model. That's called inverse modeling. Whereas forward modeling, I have a model, I want to create a data. And it's actually an iterative process. It's an iterative process. It means that I never come up to a solution unless I do it once, twice, 3 times. So how it goes, I get data from the field. This is how it works. I get data from the field. I make a model. I estimate a model. I guess a model. I get a model. I do forward modeling. Forward modeling, from the model I get data. From the modeling I get data. I compare my data, the data I got from the model, calculated data, compare them with the field observations or real data or observed data, and I compare them. How then inversion works? Where inversion comes? Inversion comes in this stage. It compare them. If they are not matching, that the percentage of matching you define. You say if they are not matching 95%, do the process. Go do the process again. Guess again a different model. Because it's tough for me as a human every time to create a new model. It's not me who creates the model. I do something called inversion. The computer will update, change, make slight change in the model to create new calculated data. The update in the model, so you have data and you update the model, that's called inverse modeling. You have data, you compare them, or you saw, okay, the difference is more than 90%. Sorry, the matching is less than 90%. There is not good match between the calculated and observed data. Observed are the one you acquired from the field, whereas calculated from your guess model, your initial model. All the inversion techniques works like that. The majority of them, there is an initial model. There is an initial model. When we go later on in the course, do some calculation with some softwares, ready-made softwares, you will find that the computer or the software is asking you, give me an initial model, an estimated model. It's fine if it's wrong, but I will update it myself through inversion. It says, okay, if there is wrong, I do it, I change it. I modify it through inversion to make the calculated and the observed match together. And it keeps checking again every time. It's an iterative process until the point that the match or the agreement is more than 59%. And once you get your final model, you will not accept it as the final or the absolute or the correct model. You need to discuss with the geologist then. Oh, geologist, I got this model. My computer gave me this model. What do you think? Is it plausible? Is it reasonable geologically to have such earth? Or such, if computer gave you 10 gram per cc, 10 gram per cc, so dense rock, there is no rock that much dense. It's all made of probably Diamond. The Earth is probably all made of diamond. Yeah, this is not possible. Then maybe you made some mistake during the inversion process or during the modeling process. That's what I mean. Check for acceptability. Oh, I got some data. My velocity is 20 kilometer per second. There is no rock which is 20 kilometer per second if you are doing seismic acquisition. So maybe there is something wrong you did during the processing technique or during the modeling technique. But there are two. And one of them is forward modeling. You guess a model. The model will give you data, calculated data. That's forward modeling. You compare them with your field observation, the real data you acquired from the field. Are they matching together? No, they are not matching. Then it's not you who will update your initial model. Let's computer update it through the process of inversion. Inversion mostly is a statistical technique. Yani it goes check where should I change in my model to make the agreement better. Inversion is simplest inversion. You know what is the simplest inversion? I give you this possibility. Let's assume this is X, this is Y. Let's assume there are many points. I ask you draw a line, the best fit line along this data. What is the best fit line along this data? There is a technique called best fit line. A technique, a mathematical technique, which draw a line where the error is the minimum. The error between all the point and this one, sorry, this one is the minimum. That's called best fit line. Excel can do it. This can be done, bro, by Excel. You have many points, you go right click on the points and say draw a line, best fit line. Behind there, it's doing some kind of simple inversion. So inversion in here, where I change my model, is some sort of similar inversion as best fit line. Basically, it's more advanced technique, but the idea is the same. The general idea is the same. So if you can program this thing yourself, you are in good shape. If you can create a program which draws for you the best fit line, you are like will be mastering inversion later on simply by yourself. I think many of you already know what is the best fit line. Maybe you have studied it or not, but at least in computer and Excel, if you have XY data points, you can click on the data points and ask the Excel to draw a line, a straight line, which is best fit line. So inversion is working similarly a little bit. And let's move. So you came up with your last model. You then come up with the geological interpretation. So in team of seismic, this is a seismic section. Don't consider this coloring and these annotations. These are made by geologists. You see this line, these green lines in here. Those are faults which were made by geologists. Usually you get something like that. This is a seismic section. And geologists then came or geophysicists or petroleum engineers even, they say, okay, I see there is a salt. They appear. This is a salt layer. This is a fault. And these are faults. They draw them and they come up simplified with a simple like schematic section. These are the different sequences, different layers, and this is how the layers are made, and this is how the structure of this section is, the geological structure from this seismic section. So the seismic section made for you a geological cross section. You define of this. This is sine rift. This is post rift. What kind of rock are they? So that's how is it. What is the age of these of different rocks? Post rift, sine rift, pre rift. They are all made from the seismic section you have without those annotations. Those annotations made by interpreters who interpret seismic data, geologists, geophysicists, even petroleum engineers. And tie up a lot of data and correlate them with outgroup. If you have an outgroup in the area, correlate your model or your geological section you created with outgroup. Try to find a borehole and correlate your borehole with this seismic. If you have, for example, a borehole in here, the borehole is supposed to give you the same layers. And you in the borehole, you at least already know each layer and what it's made of, and correlate it with your seismic section and this borehole. To integrate all of these together during the phase of geological interpretation, when you are doing interpretation. When you do visualization, let me see. Okay, I think this is enough because I'm left with almost 10 minutes. I would like to for you to ask questions for anything which is not clear. Do you have questions, guys? Guys, any questions you have? Are you following along with me? Is everything clear? Be honest. You find it difficult? Maybe because this is just the introduction and things are new to you. The terminology itself, geophysics, is new, and the things I might discuss might be complex a bit, but the idea here, don't go to the details. Try to understand the basic concepts. If you go through the slides yourself without referring back to my lecture, you find yourself lost. So for the one who haven't watched the lecture yet, I recommend highly that they watch it, they open the slides and watch as well the lecture. Otherwise, nothing is very clear because those are just bullet points, some explanations. Without knowing what I'm talking about, it's not clear. Many things you find here, they are not available in your slides. Some of them they are available. For example, this is available, this is available in the textbook, I mean. Whereas non-uniqueness is not there. I just brought it up because it's a very important concept in geophysics. The resolution, forward and inverse modeling, it's somehow mentioned in the textbook, but not clarified. If you read it yourself, you might not be understanding it. You'll be lost. Finally, geological interpretation will work out ourselves with every method. We'll come up to that stage. We do geological interpretation. The final result is geological, relate everything to the geologist or to geology again, because that's what we are interested in, to study the geology of the earth in a from different dimension, from different perspectives than what you used to. That's how geophysics helps, and that's the importance of geophysics. No further questions? Anybody have a question? In case if you don't have question, I will stop recording. And let me see how many slides left. There are just few slides. 1, 2, 3, 4, 5. Maybe I modify them slightly and remove anything which is not very important. Thank you very much. I will stop recording.